everyone. Thank you for being patient with us while we're sorting out some technical issues here. We're now ready to proceed to the next session, which is Test of Time award paper. Every year, ICML looks back not just at the papers that made a splash when they came out, but at the ones that had a lasting impact years down the line. So this year, the selection of the award was chaired by Professor Kilian Weinberger, who was also a program co-chair of ICML 10 years ago. So all the papers accepted to ICML 2016 were considered. And the selection process considered highly influential papers based on citations and scholarly influence. So in the end, there's one paper that emerged as a clear winner, which is Asynchronous Methods for Deep Reinforcement Learning. So this paper pioneered asynchronous RL, which has been a major contributing factor to the success of RL in LLM post-training and has really reshaped how RL is used in practice. And so today, the lead author, Vlad, is also here with us in the room, and I would like to invite you to go on the stage. The organizing committee has also prepared this award certificate, and now I would like to hand over to you on behalf of the program committee. Congratulations to you and your co-authors. Now the stage is all yours.
Okay, thank you for that introduction. I'd like to start off by thanking the program committee. It's really a tremendous honor to have this work recognized, especially alongside all the amazing papers that have won this award in the past. I would also like to thank my co-authors here. Unfortunately, I was the only one who could make it in person, but Adria will join us virtually later on in the talk. So we'll tell you a bit about the backstory of the paper, describe the work at a high level, and give some thoughts on what we thought the impact was. So because this work is 10 years old, I think it's good to start off with setting the context. So while the paper came out in 2016, most of the work that went into it happened throughout the course of 2015. So what was 2015 like? I would say that this was still the very beginning of the deep RL boom that followed. So there was growing excitement around combining neural networks with reinforcement learning following the publication of papers like DQN, TRPO, and other early works. What's probably hard to appreciate, even if you go back and read the older papers, is how separate some of the communities were in machine learning. So I would say that was very much the case for reinforcement learning and neural networks. So on the RL side, there was still, some long-standing worries about nonlinear function approximation and using RL with neural networks. This was based on a number of empirical and theoretical results that highlighted the potential pitfalls of this combination. There were also worries on the other side. For many people, RL was kind of a mysterious thing. Maybe you learned a little bit about it in your machine learning class, but it was, I think, not nearly as much a part of the standard toolbox. And many people thought RL didn't really work. Just a few years earlier, I was discouraged from working on RL by a few potential PhD advisors. So finally, in 2015, I think the arcade learning environment released by the University of Alberta, which exposed classic Atari games as RL environments, was starting to emerge as a standard benchmarks for the field. So while it was a big step up over the carefully designed toy problems that early RL papers tended to focus on, it came with a lot of additional computational demands for the work. So when this paper came out in 2016, it was probably a bit of a surprise to many people because half the authors of this paper also appeared on the DQN paper.
Thank you, Vlad.
And while DQN advocated for the combination of Q-learning,
한 번에 상쾌하고 시원하게 기름진 비듬 가려움까지 한 번에
this paper diverged from that philosophy almost entirely. It said, let's use CPUs and almost completely off-the-shelf RL methods. So why did we diverge from the DQN recipe? So there were a couple of reasons for that. We did want to build on top of DQN after it came out. We wanted to explore richer environments and new research directions like episodic memory, intrinsic motivation. But at the time, DQN required something like 1 week of training on a single GPU per game. And again, in 2015, I think DeepMind had migrated away from using its own compute infrastructure to Google systems. And at the time, Google did not yet have GPUs available for model training in the internal data centers. So we simply couldn't do the research we wanted on the available hardware. Now, of course, what Google did have were data centers filled with multi-core CPU machines. And we quickly discovered that you could actually run quite a few training jobs, especially if you were okay with using a single machine and if you were okay with having your job periodically, preempted and restarted. So this turned out to be a great opportunity. Now, the second reason for the diverging from the DQN recipe was curiosity. When we developed the original DQN algorithm, DeepMind itself only had about 24 GPUs for the entire research team. So we never got to fully explore the spectrum of RL algorithms. We started with Q-learning,
Thank you, Vlad.
made it work, and kind of
Having
ran
seen
with
all
it.
the results
So
just
now with
mentioned,
the
we consistently
additional
see
compute
that one of
resources
the
of
algorithms
Google, we
is
wanted to finally go
outperforming the
back
rest.
and explore things like on and off policy learning, value-based versus policy-based methods, and so on. So let's move on to the ideas in the paper. So one of the key contributions was this framework for parallel asynchronous training of reinforcement learning agents. So in this framework, there are k separate actor learners, each running in its own thread on a multi-core CPU. And each actor learner would have its own local copy of the weights, and it would use this local copy to interact with its own independent copy of the environment. Here, maybe an Atari game. So it would generate experience and periodically use its local copy of the weights to compute a gradient update. And it would then apply this update to a global, shared global copy of the weights that was available to all actor learners. So crucially, these updates were done without any read or write locking. So this is known as the hog-wild learning setup, which itself won the Test of Time Award for, I think, at NeurIPS 2020. This helped maximize learning throughput without really harming the progress of the algorithm. So this was a very simple framework, and it allowed us to experiment with a number of different RL algorithms. We were using Lua at the time, and we could implement a basic parallel Q-learning agent in about 100 lines. So this really was incredibly simple to work with. So in the experimental part of the paper, we compared 4 different reinforcement learning algorithms in this framework. 3 of them were essentially off-the-shelf methods: one-step Q-learning and SARSA, which used one-step return estimates. We also used n-step Q-learning, which used n-step return estimates. The 4th method was the advantage actor critic, which you will hear more about in a few slides. So we compared these methods to DQN on a number of Atari games, and we found that all of them actually worked surprisingly well. So here you see training curves on 5 Atari games. X-axis shows training time in hours. The Y-axis shows the scores. DQN is shown in blue and ran on a GPU, while the other methods ran on 16 core CPUs. So while the exact scores don't really matter, I think these results were notable for a couple of reasons. So first, as I said, all of these methods, all the asynchronous methods, work surprisingly well. They all either matched the performance of DQN or substantially exceeded it in terms of learning speed. The second reason these results were notable is compared to DQN, it shortened the research loop iteration cycle from 1 week of training on a single GPU to 1 day on a multi-core CPU. So this both allowed us to iterate faster and to run more experiments at once. This was huge for us internally. A lot of projects used this framework and explored a lot of interesting ground in RL research. But I think it also made reinforcement or deep reinforcement learning research more accessible to the wider field. This allowed labs that maybe didn't have any GPUs to perform meaningful RL experiments. So if you look at the results a little more closely, you'll also notice that one of the methods actually tended to work much better than the others. And I will now hand it over to my colleague Adria to tell you more about this method.
Thank you, Vlad. Having seen all the results just mentioned, we consistently see that one of the algorithms is outperforming the rest. And for that reason, for many people, this work became known as the A3C or the A to C paper. So what is A to C? The advantage actor critic algorithm works in the following way. We start from a reinforcement learning setup with an actor and a critic. A single model with a set of weights outputs a policy and a value function prediction for a given state, which aims to estimate the expected sum of future rewards. The actor collects transitions from one observed state to the next by sampling from the policy to act and interact with an environment. With those transitions, A to C does three fundamental computations. The first one being advantage estimation. So we estimate the advantage to measure how better or worse a given action is compared to the average for a given state. There are many ways of doing this. A simple one is a one-step estimation. We look at the reward that we obtain after having performed the action at time t, and we add the discounted value function at time t plus 1 to it to estimate the sum of future rewards from that point onwards. Finally, we compare the resulting quantity to the value function at time t. We can extend this to k-step transitions, where we add all observed rewards from step t to t plus k minus 1. And we estimate the future rewards from t plus k onwards by using the value function. And then we compare all of this with the value function at time t. This is similar to a generalized advantage estimation, although in this case we explicitly compute and bootstrap at time t plus k. This provides us with a mechanism to trade off variance and bias. So if we use a high number of steps, the variance is higher, as using more rewards introduces variance. And if we use a low number of steps, the bias is higher because we rely more heavily on our value function estimates. In E2C, we use a mix of different values of k, mainly due to two reasons. The first one is that it's very practical since we perform updates every t max steps. It is simple to implement. And secondly, we also make the model a bit more robust to different sorts of bias variance trade-offs. So going back to the A to C slide, the second formula we have is the critic update. So we minimize the advantage, that is the temporal difference error, to update the baseline value function weights. Essentially, the critic learns to accurately predict the expected return from any given state. Finally, we have the actor update. The actor optimizes the policy weights based on the critic's feedback using the policy gradients loss with the advantage we just computed. But crucially, we added an entropy regularization term here. By encouraging the policy to remain somewhat stochastic, we ensure that the agent continues to explore the environment rather than collapsing into a suboptimal deterministic policy too early in training. Now, I'd like to highlight a few points of A to C. First, an implementation detail that is worth reiterating. The entropy term is important. Others had observed similar conclusions in related work, And this was important an important term to include in practice in our experiments. Secondly, as we saw in previous performance tables, it delivered very strong results, and it did so in almost every environment that we tried. In fact, the results were a good segue to try different environments, like visually different and 3D, like Labyrinth and Turks that I am showing on this slide. This was a big step beyond the visually simple Atari games. And finally, I'd say perhaps the biggest strength was its simplicity. So the entire algorithm essentially boils down to two clear intuitive formulas, one for the actor and one for the critic. This made it very easy to reason about and debug. So why has the A3C paper been influential? We attribute this lasting influence primarily to two factors. One is its simplicity, as mentioned, and the second is the fact that it proved that on policy, no replay algorithms were completely viable at scale. This simplicity directly drove reproducibility. If you compare it, for example, to the QN, which had a whole page of hyperparameter settings to tune, A3C had very few. And this made it highly accessible, and both from an engineering and research point of view. And it quickly became like the de facto reference point for actor-critic methods. This in turn led to a massive number of open source implementations, but also internally at DeepMind at that time. Apart from this, its simplicity made it an ideal starting point for new research. When we look at scaling reinforcement learning, A3C proved that this paradigm just kind of wanted to work, so to speak. It scaled beautifully with data and brought RL much closer to standard deep learning practices, paving the way for large-scale systems like Impala, Apex, and AlphaStar. And it also sparked away from algorithmic improvements. We saw the development of policy corrections, like as done in vtrace and retrace, and many other algorithms that also appeared that used scale, such as PPO, although influenced by other work, of course. Finally, other components of the network were explored to tackle different task complexities, with auxiliary tasks as done in Unreal and memory as done in neural Turing machines. Overall, A3C provided a stable, scalable baseline that made a great starting comparison point. Now, back to you, Vlad.
All right, thanks to Adria. So, while it's been really fun to, pat ourselves on the back here, I think it's also good to take some time to reflect on, maybe what ideas didn't age as well from the paper. So as we mentioned, A3C did scale really well with compute, but we found that it didn't scale as well with model size. And I have this old tweet from Andrei Karpathy highlighting this. This wasn't necessarily specific to A3C or asynchronous methods, but it was a finding that all the advances in convolutional networks from the mid-2010s didn't seem to help in RL. ResNets, batch norms, none of this helped, and it was kind of puzzling. So again, while this was not specific to A3C, I think one design choice of our framework did exacerbate the problem. So we eventually realized that as we used larger models, it took longer to generate the experience and to compute the gradient updates. And you ended up with stale gradients by the time you applied them to the shared weights. And once you have a stale gradient, I think there's not a whole lot you can do with them. You can throw it away, but then, what's the point of generating all this experience? So the Impala paper, which followed a few years later, I think solved this in an elegant way. It showed that, yes, parallel asynchronous experience collection is a good idea, but you shouldn't communicate gradient updates to the centralized model. You should communicate the experience itself. Now, of course, you still have a staleness problem. By the time the experience makes it to a centralized learner, it will have come from an older version of the policy. But as Impala showed, you can effectively correct for this using an off-policy correction method based on importance sampling. And I think here Impala really unlocked large models for DeepRL, and from there on you could scale both with compute and model size. So to wrap up, a few final thoughts on I think the key themes here. So again, one is that constraints can drive research forward. If we had access to more GPUs at the time, we probably wouldn't have done this work. The second point I think goes back to simplicity, and as Adria pointed out, these small, carefully tested changes can have a long-lasting impact. So if you look at this paper, honestly, there isn't all that much new stuff in it. It's essentially a combination of existing ideas that was carefully tested. But nevertheless, it did have a lasting impact. And I think, to quote Ilya Sutskever, this was a case of, minimum innovation for maximum impact here. And I think, despite its simplicity, I think maybe it did convince more people that RL could work, and RL with neural networks isn't that scary. And finally, when I go back and look at these experiments, one thing that jumps out to me is this, the results did show this clear case for scaling. There were very predictable gains from more compute. And I think maybe, looking back, we didn't even appreciate it fully at the time because, there might be multiple reasons for that. But, Rich Sutton's bitter lesson came out a few years later and made this case that, hey, these methods that want to learn and can take advantage of data and compute, win in the end. So I'll end here. Thanks for your attention, and hopefully there's time for some questions.
更多演讲实录与文章已收录至雷锋网ICML 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码，或进入雷锋网ICML专区即可查看。